In this video, we're going to talk about the Gibbs energy and equilibrium. Normally when we think of the free energy of a system, we're talking about a reaction, doing one thing, going one way. If you had N2 gas plus 3H2 gas, making 2NH3 gas, you could solve the delta G for this reaction as written. Really quickly, if we wanted to do that, the delta G naught of formations are 0 for elemental materials and minus 16 kilojoules per mole for ammonia. So two products minus reactants. The delta G of this reaction is negative 32 kilojoules per mole. This implies that it is spontaneous. It should make our products. However, remember what delta G really is. Our delta G is the negative T delta S of the universe. Delta G is telling us the maximum work that we could harness if this reaction goes to completion and we were to harness as much available work as we could as the energy is redistributed during the reaction. Now we've talked that you'll never really harness that much work, but additionally, we need to focus on the idea that you'll really never do that much reaction. Just because something is spontaneous doesn't mean it's going to go to completion. Something can sit around waiting to react for ages. Part of it could react and then the rest not for a while. How long it takes a spontaneous reaction to occur is not clear. Diamonds technically can't exist on the surface of Earth. They will convert back into graphite. It is a spontaneous reaction that they will favor doing that. And yet, if anybody has a diamond ring or earring or something, it's been around for millions and millions and millions of years, and it's going to be around for millions and millions and millions of years more. Spontaneity doesn't talk about how quickly something occurs, or even that it goes to completion. Really, what happens is you have your particles bouncing around, colliding, various things can occur. When our N2 and some H2s all collide with each other, it's possible they can make two NH3s. And over time, this would keep occurring and more would get formed and make more NH3s. But these particles are continuing to bounce around. They zigzag and they hit the walls and they bounce into each other. It's possible two of them can combine and go backwards. The truth is, this reaction is an equilibrium reaction. If we think back to activation energies and the like, you've got some starting materials, you've got some products. So an exothermic reaction here, there's an activation barrier that we have our energy of activation. And we have a bunch of particles at some intrinsic energy, and then due to thermal energy, they've got a spread. Most are lower, but a few have a bit higher. So the idea of the entropy in the microstates. As we distribute the energy, sometimes a few are just going to have more, sometimes a few are going to have a little bit less. Well, some of these particles are high enough to make it over. And every one that does, well, the remainder redistribute their energy constantly through the various possible microstates, and eventually some are high again and they go over, and some are high and they go over. And over time, you'll make product. You'll start building up product. Well, the product has its own thermal spread. Most are low, but a few will be high enough to get over, and technically there'll be even more over here on the starting material side. But a few randomly of your products, just due to the distributions of energy, will have the energy to go back. Depending on the difference of your delta H, the return may be far more difficult than the forward reaction. Or, if it's endothermic, the return might be easier than the forward reaction. Depending on what your delta H is, this will adjust how readily your forward and reverse reaction can occur. The rates will be different. Well, our rates are also dependent on concentration. The more of this that transfers over, the less particles there are to do the forward reaction, and the more there are to do the reverse reaction. Remember that for rates of reaction, concentration is a factor. The greater your concentration in a simple reaction, in general, the faster that reaction goes. So as we build up products, we will have some material go backwards just by random chance, even if that is disfavored and non-spontaneous. That is, spontaneous reactions is that over time, we will favor going in the spontaneous direction. It is the statistical argument for the mole of material in all of its microstates. On the individual molecule level, you really can't apply this. It is perfectly fine for two ammonias to slam into each other and make N2 and H2, despite that would have a positive delta G. It's not particularly likely, and over time, you will definitely favor going to make ammonia instead of to break apart ammonia. But at any given one moment, looking at two ammonia molecules, they may simply both have enough energy to get over the hurdle and go back. Most do not, and so most won't do this, but it is possible to have a few. What this means is that our reaction never really goes to completion. We don't harness all of the possible free energy. And in fact, we are opposed by the reverse reaction, just randomly having some of its molecules go backwards. As a result, the actual free energy of the system here is going to be equal to what it would be if it could go to completion, modified by the equilibrium potential. Q is our reaction quotient. Remember, in equilibrium, we have our Q values and our K's of equilibrium. Depending on what our mixture is at this moment, it's going to interfere with the maximum amount of free energy that could be released if none went backwards and the reaction was allowed to go to completion. So what your actual free energy is depends on the mixture at any given moment. Let's look at an example here. Well, this is about equilibrium, so let's look at equilibrium. At equilibrium, you will no longer change your concentrations, which means you can't be going to the right or to the left. Neither direction will be favored over time. If you're at equilibrium, you must have reached the point where you have no more free energy. Neither direction will be favored. If my free energy was positive or negative, I'd favor one direction or the other in the reaction. But if it's zero, then I won't change my concentrations any further. And this is what it would be like at equilibrium. So zero must equal the free energy for the reaction if it could go to completion plus RT ln, and at equilibrium, Q equals K, which is often just shortened as K in these free energy equations. So there's some mix. It's the mix that we will have at equilibrium. We can rearrange this a little. The standard state free energy of the reaction is going to be equal to the negative RT ln of the equilibrium constant. When you have an equilibrium reaction, because there is a little bit going back all the time, we can actually determine what that will be based on the free energy of the reaction. Despite that we'll never use it all, the driving force that it has lets us know where this equilibrium needs to be to counteract it. Let's take a look then and actually calculate out an equilibrium constant. If I have N2 gas plus 3H2 gas in equilibrium with 2 NH3 gas, well, my delta G naught, again, was 0, 0, and minus 16, so the delta G naught of this reaction was negative 32. So negative 32,000 joules per mole must equal negative 8.314 joules per mole Kelvin times the standard state temp we're working at of 298 Kelvin, ln of K. We can divide by RT to move it over to the other side, and the natural log of my equilibrium constant must be the delta G naught of the reaction divided by RT at 298. Calculate this out. 13.32 will equal the ln of K. E to the 13.32, or E will cancel the natural log, and E to the 13.32 will equal our K, which will equal 6.09 times 10 to the 5. This is very favorable. We should have lots of products and very little reactants, and our delta G says, oh, it should definitely be spontaneous. We should be able to make ammonia quite readily, at least energetically. Unfortunately, this reaction is so slow that if you actually put N2 and H2 in a container and leave them, they will still be there many decades later. The only way to get this reaction to go is to heat it up. About every 10-ish degrees tends to double the rate of reaction, and you need to get ammonia production up into the 700 or 800 degrees Celsius range to start producing ammonia, at least with old catalysts. Unfortunately, as a result, well, our temperature gets larger. If our temp gets larger, our ln of K gets smaller. As the ammonia reaction is heated up, we actually favor the starting materials more than the products. This is one of the big problems with the synthesis of ammonia back before World War I. Very few methods were efficient by any mean until the Haber-Bosch reaction came along, which could do it at a much colder temperature. By having a catalyst that lowers that activation energy, instead of the original quite large one, you could make a lower activation energy. You could perform the reaction at a colder temp, but still have it turn into ammonia at a reasonable speed. And the lower your temp, the more it favored making ammonia. We'll dive further into free energy and equilibrium in the following videos. But what we want you to see here is that the free energy of your reaction can be used to calculate the equilibrium constant for your mixture of products and reactants.